and welcome to this lecture. So we've already looked at two important methods for designing estimators, coming up with estimators. One was this method of moments way of deriving estimators. The other is the maximum likelihood approach. Both interesting approaches. They give you different types of estimators. We saw a lot of properties. So we're going to continue looking at properties. In particular, we will start looking at a property called consistency of estimators. We won't go too deep into it. I'll just mention a few properties, give some I'll simply define this property and give a few examples of when consistency is there, when consistency is not there. We won't go too deep into this. This is a little too advanced for this course, but I think this word consistency is important to know. Okay. So here is a problem where you have n IID samples from a distribution and there is an unknown parameter theta. There is an estimator theta hat for it, and the error, we have seen this error random variable before, which is theta hat minus theta. So error is a random variable. So generally we expect as n increases, as you observe more and more samples, this error should take values which are only close to 0, right? It should take very, very small values. So in some sense we are expecting some convergent behavior for error converging to 0 in some sense with n. When n increases, you are expecting some convergence to 0. So how do you capture this mathematically? It turns out the following requirement is something that conveniently captures it. The probability that absolute value of the error is greater than delta. Okay, so that's a number, right? So this probability is just a number, right? So this is a number. Okay, it can be between 0 and 1, right? And as n increases, it depends on n. That's the most important part, right? And I mean, you don't want to have something independent of n. You want it to depend on n first. And as n tends to infinity, I want this number to go to 0. Okay, it should become smaller and smaller and smaller with n. So what does that mean? If you observe more and more samples, as you keep observing more and more samples, probability that your error goes outside of this minus delta delta for any delta can be any small number. Okay, so you can visualize if you like on the axis. So there is 0 and then there is minus delta delta, and I want error to be only here. Error should be here with probability approaching 1. Okay, so probability that it's outside of this should approach 0. Okay, so that's the condition. So if an estimator satisfies that condition, it is said to be a consistent estimator. Okay, so this word consistent is used in this context. This requirement also has a technical name in probability. It's called convergence in probability. If this is something that you'll see in many statistics textbooks, this word convergence in probability is used. This is what they mean. So if they say the error is converging to 0 in probability, they mean this. Okay. So this consistency of an estimator in terms of the error converging to 0 in probability is a nice requirement to have. Okay. So let's look at bias and consistency through an example. Here is the situation. I'm looking at IID samples according to some distribution, and there's a parameter that I'm interested in. It's the mean of the distribution. Okay, mean of the expected value of x, mean mu is my parameter of interest. Okay. So one estimator I can think of is just M1, this capital M1 I've been thinking about, this x1 plus x2 plus xn divided by n, the sample mean, right? This estimator is unbiased, right? We know it's unbiased. If you take expected value of mu, it becomes equal to mu. You can prove that quite easily. And this estimator is consistent. And the proof is simply weak law of large numbers. Remember, the weak law of large numbers essentially says that this guy, this x1 through xn divided by n, if you call it something, the probability that absolute value of m1 minus mu, so if we prove it using some Chebyshev inequality and all that, right? So this greater than some delta is going to be less than or equal to some quantity that tends to 0. Tends to 0 as n tends to infinity, right? So this was some proof that we did using Chebyshev inequality and all that. And this is just shows consistency. Okay, so in fact, the weak law of large numbers generally says sample moments. Okay, so this is an important fact to remember. sample moments converge to distribution moments, assuming they are all finite and existing and all that, as n tends to infinity. So, this convergence is in probability, okay, the previous sense that we looked at. Okay. So, this fact is something very nice to remember. So, sample moments will converge to distribution moments as n tends to infinity in probability. So, this is something that one can use very well to do this. Okay. So, here is a slightly modified estimator where instead of dividing by n, I am going to divide by n minus 1. Why? Just for fun, okay, just to show you that all sorts of all sorts of combinations are possible. This estimator is a biased estimator, it is not unbiased. Why? Because if you take expected value, you will get n mu by n minus 1, and that is not equal to mu. So, it is biased, but even though it is biased, it is consistent. Okay. So, bias and consistent, it is not like they always go together, only unbiased estimators are consistent, that is not true. Okay. Here is a biased estimator which is still consistent. Okay. And in fact, the other type of example is very easy to come by. I mean, if you have a simple estimator like x1, I'm just going to estimate it as x1. I don't care about all the other samples, throw all them away, just x1. So, this is an unbiased estimator, but it is inconsistent, it's not consistent, right. So, it's not going to, the error is not going to converge to 0, error is going to be some p or something. It's a fixed distribution, it will not for any, I mean, there's no dependence on n, right, n doesn't even enter the picture. So, there's no question of error going to 0 with n. So, this is a very bad estimator, it's unbiased, it seems like, okay, oh, that's a good property, but then it's not consistent. Okay. So, what is the point of the slide? The point of the slide is to show this bias and consistency, all sorts of possibilities exist. There can be unbiased estimators that are consistent, unbiased estimators which are not consistent, biased estimators which are consistent also. Okay. So, all these combinations are possible. So, you will see quite often in textbooks and statistics, when they discuss a estimator, they will worry about whether or not I can have a biased estimator or unbiased estimator, which is better, can it be consistent, can it not be consistent at all. These are things that people will worry about. Okay. So, this is a basic course, we are not going to go too deep into things like consistency, but the fact that all sorts of combinations is possible is something that you should be aware of. Okay. So, here is a general result on method of moments estimators and also on maximum likelihood estimators. Here are some general properties you can prove. We won't prove any of this in this class, but at least to know it will be good. Okay. So, usually if you take method of moments estimators, if the quantity you are estimating is already a moment, then you will have unbiased behavior, right. So, if you are estimating the mean, the method of moments is going to give you an unbiased estimator. If you are estimating the variance, the method of moments will give you an unbiased estimator. So, if it is directly a moment, then you will get some biased behavior, which is good unbiased behavior with method of moments. But in most cases, most of the other interesting cases where the parameter is not directly a moment, you will have bias. Okay. So, there will be bias in method of moments in most cases, and you can go back and look at our examples. You will see in most cases we got biased estimators. Okay. But on the other hand, in typically you can expect them to be consistent. Okay. So, why is that? Because sample moments converge to distribution moments in probability. We saw that before, that comes from the weak law of large numbers. And how do you find the method of moments estimate? You equate sample moments to expression in terms of parameters, and then you invert that, right, to get parameters in terms of sample moments. Now, if that function of sample moments is continuous, if it's a good, smooth, continuous function, then just because these sample moments converge to distribution moments, your MME estimate will also converge to the expected quantity, and then you have a convergence and error will go to 0. Okay. So, they end up being consistent. You can show consistency for method of moment estimate if your function ends up being continuous. Okay. That function being continuous is critical. There are some cases when the function won't be continuous, it will go off to infinity, here, there, somewhere in the middle there will be a break. In that case, then you can't rely on that, but in many cases it will end up being consistent. Okay. So, interesting that even though it may be unbiased or something, and it may be biased, it's likely to be consistent also. So, this is possible, but one needs to check these things. Typically, if there is a continuous function of moments, then it ends up being consistent. Okay. That's a good thing to know. Now, maximum likelihood estimators have a rich set of theoretical properties. Lots of very interesting properties that they satisfy. You can show that they are consistent, You can show that bias will vanish in a limiting sense with n. So asymptotically they end up being unbiased and consistent. Okay, so of course the many maximum likelihood estimators will be biased. You see that they end up being biased for some reason, but nevertheless the bias will go off to 0. They have very interesting properties. A very interesting property is this functional invariance property. If you have a maximum likelihood estimator for theta, then any function of theta, you have a direct maximum likelihood estimate, right? So you can just put g of theta hat, you get the estimator for g of theta for maximum likelihood, all these kind of very powerful properties. So that's why maximum likelihood estimators are very popular in theory. You can prove a lot of very interesting properties. Okay, so all these properties are something that are there. I'm just doing it so that you hear these words in these lectures and you're not surprised when you see them. We won't go into great depth or detail on any of these properties. What we'll do very quickly to round out this properties section is to look at one way of comparing estimators. Okay, this is a very popular way to compare estimators. This is to compute the squared error risk, okay, or which I called as mean square error. So you compute this for so if supposing you have two competing estimators, right? Estimator 1, estimator 2. You find the squared error risk for first estimator, squared error risk for the second estimator, and pick the one that is better. Okay, so this is something that's quite common. And it seems very logical and reasonable, and that leads us to study this MSE or risk of estimators. Okay, so so given the distribution, one can compute the risk quite often. Numerically, maybe you can compute it, but definitely, theoretically also it's possible to compute if you can do some expectation computation. Okay, so I'm going to show you one example to highlight how two estimators can have different risk, very different mean square error. Okay. So I'm going to look at this uniform 0 theta samples and two different estimators for theta. One is the method of moments estimator, which was just 2m1. You can see bias is 0 for this, so risk becomes equal to variance. And if you want to find the variance of this, you can do the calculation. Let me not repeat it here. You will get theta squared by 3n as the risk of this estimator. Now the second one, max of x1 to xn, the calculation is a little bit more involved. But look at this number that you get, look at this risk that you got for MME and look at the risk that I am getting for ML. Notice the huge factor of 1 by n, okay. So the ML decoder is 1 by n better in mean square error than the MME estimator, okay. Let me repeat that, the ML estimator in this case for uniform 0 theta is factor of 1 by n better than the MME estimator, method of moments estimator, okay. And n can be 1000, right? You may have 1000 samples, and look at that, 1 by 1000 is a huge factor of improvement in the error, okay. So this kind of calculation is also really interesting, for two estimators for the same problem. You want to prove that the risk of one is better than the other. Okay, so here we did some calculations with some known distributions and all that. Supposing you don't have all that, or you don't want to do it, or you're maybe it's just too involved a calculation. Quite often the calculation will become so involved that you can't do these things theoretically and cancel out and figure out what it is. Okay, here in this case it worked out very neatly. May not work out the same way in general. So what will work in most cases is a Monte Carlo simulation. Okay, so if you want a quick and dirty estimate, you vary n. You do n equals 100, n equals 1000, n equals 10,000, n equals 1 lakh, I don't know, lot of n. Then you simulate over and over and over again, repeat 100 samples some 1000 times, you repeat it, generate 100 samples, do one estimator, do the other estimator, and then you can compute the risk. You can compute the risk on your simulation and plot it versus n and see which is doing better. Okay, so that's sort of the Monte Carlo approach, and it's an interesting Colab exercise. We'll look at it if we have time to build a Colab notebook for this. And this is also something that's very important and interesting when you compare estimators. So if you want to compare two estimators, you want to show one has better risk than the other. Okay, you pick a risk of choice. Usually the squared error risk is a pretty good choice. You have to show one is better than the other. You can do it theoretically if you're well versed with these expectation calculations, or you can do it using simulations. Some people like the theory better, some people like the simulation better. Either is good enough, and you can compare for yourself and conclude which estimator is the better one. Okay, so that's the end of this lecture. Hopefully you got a flavor for some of the topics that are coming in. There are two different ways that we have seen so far in approach of design of estimators. One is the method of moments approach, the other is the maximum likelihood approach. We will see one more a little bit later. But there's all these kind of interesting properties that you can study for estimators, and the most interesting, in my opinion, is this risk, squared error risk. The squared error risk really captures what you need from an estimator, and practice, you may not be able to calculate it in many cases. In that case, you can at least do simulations and satisfy yourself that the estimator is working. Okay, thank you very much.